So what I want to do today is to just talk a little bit about Bernoulli, as we dealt with last time. Talk about Bernoulli not in a straight line, but perpendicular to streamlines, and then talk about these individual components here in terms of how we use it, stagnation points in terms of calculating pressures, how we measure pressures and continuity. So we won't get through all of that, I'm sure. But let's just regather our thoughts from where we were last time. If you remember where we were last time, the main event for us was that we figured out exactly what this expression was. And what we could do, if we wanted to, if we, for instance, the more usual way to look at this, I think, is if you divide through everything by g, in which case this becomes 1, and you end up with, and if you ignore the integral, so the reason for this integral is if unit weight isn't constant with pressure, as it is in a gas, as we know, then you have to actually account for that. But if the fluid is incompressible, which is what we said was one of the requirements for Bernoulli, then this integral is just P over the unit weight, right? And so we can also write this as pressure divided by unit weight plus V squared over 2G plus elevation, Z, is constant. And so what that refers to is that along a streamline, as you go, you could calculate the value of this magnitude here, you could calculate the magnitude of this combined term here, and they should both equal the same physical amount. And so the idea typically is, if you know the behavior at this point, you could calculate for one missing parameter at the other location, because you know that they're equal to each other. And that's what we're attempting to do. And so we'll apply that a little later to the Jackass video, just to figure out exactly what kind of what the unknowns are in that system. So the other part of what we'd like to do is to say what happens if, instead of going along a streamline, like we do here, if we have some kind of parallel streamline and we want to go from one location to another. And so what's different here is, in this particular case, you can imagine that if you look at this, there's some kind of radius of rotation on here. And in the same way that we did the tennis ball thing, I won't get there, is if you think about this, is it's physically rotating around a point. And so in the same way as if I swing around, happens to be fluid on the end of this, my arm's being stretched by this weight. So you can imagine that there would be some tension on my arm, and that, if you translate that into water, means that there'd be some change in fluid pressure as you go in the trajectory that links these 2 points. And so that's what we'd like to be able to evaluate today. And so what we'd like to end up getting, this is by far the most important of the expressions we'll use in this course, I would say. So don't forget Bernoulli, in a straight line, along the streamline. But what we'd like to figure out is exactly what this is. And so rather than use the 2 pages of derivation in the notes, let's just do a very simple manipulation to be able to get from what we know to what we'd like to be able to apply. And the manipulation is basically this. We know from what we've done already that the pressure change radially in a fluid is this, right? So this basically says, from these examples that we've done, if you're spinning a can of water around some center line, then we know something about the free surface of this, and we ended up developing some equations for angular motion. So we've seen this before. So what we can do for this particular case is that we could look at this system here, and we could look at some angular rotation, which is omega, which is the rate at which it's turning in radians per second. And we can look at some radius, r, which is where the point is that we're looking at. And we could look at some velocity, and this is v theta, which is also the velocity along a streamline, right? So the one thing we do know are the velocities on these streamlines, because this is the streamline velocity that we're using in this condition here, right? This is the streamline velocity. We've got rid of these xy coordinates for a moment, and we're looking at behavior along the streamline. So what we could do is we could look at the magnitude of this velocity as equal to v theta is equal to the radius times the rotation rate. You just do that by looking at this length multiplied by the rotation rate, and that gives you this velocity along this line. And if we do that, then what we can do is we can also write this as, jumping around. So if we know this, we can also write the rotation rate in terms of a velocity. And so that will be that the rotation rate is equal to what? Velocity along the streamline, which is the same as this, divided by r. Or alternatively, the squared of this rotation rate is v squared s over r squared. And so what we can do is we can put that in here. And if we do that, we end up with dp dr minus rho r. This is velocity in the s direction squared over r squared. Nothing more than that. Get rid of this, get rid of one of these, still equal to 0. So that's it. We haven't done anything to violate that so far. And we could also now rearrange it to just multiply by dr, right? So if we multiply by dr, we end up with the change in pressure minus rho times velocity along the streamline squared divided by r and multiplied by dr. Is that right? Over we go. Is that right? Yeah, peaceful. And so if we have that, still equals 0. And we could integrate that, both sides. And those aren't very good integrals. But if we integrate that, and we also divide through by unit weight, rg, rho g, and rho g, then what we should end up getting is p over unit weight, which is just rho times g, plus the integral. We're going to lose densities here, and we're going to end up with streamline velocity squared over rg dr, which we haven't integrated. And so the other thing that we can also do to this is that we realize that the direction r is radially outwards from this center of rotation that we have. So in the book, and in all of these cases, what we'll do is we'll define a different direction, which is dn, which is in the opposite direction of r. So in other words, we can also write that in the normal to the streamline boundary that points towards the center of rotation, this is the same as minus dr. And if we make this substitution here as equal to minus dn, because that's what dr is, then we end up with an expression which should be this, which is p over unit weight plus an integral v squared over, let's call uppercase R, g dn. And so this is this. And we haven't included the self-weight of the material, so let's just add that. So we can't actually do it with this simple analysis. And this has to, because we've integrated it, this actually should be a constant, right?
Where did you leave the row at?
What happened to what? Say it again, sorry.
You got rid of density. Where did it go?
Where did density? It canceled out top and bottom. So we multiplied, we had density, We multiplied top and bottom by rho times g, rho times g. So this density went out and this density went out. Okay? Was there another question? Oh, so there should be density there. That's your. Oh yeah. Okay. So if you divide this through by rho g, divide this through by rho g, divide this through by rho g, which is actually unit weight, then you end up losing this. You end up losing this, and this is p over density. So this is the same. This is the same. This is v squared rg, v squared rg times dn, and this is unit weight. Okay, this is, okay, is that what you're telling me?
Yeah.
Thank you. Okay. So, good. Excellent. Good. And so this is basically the same analogous expression to the linear one, but it means that if we hop from one streamline to another, we can calculate the changes in pressures typically as we go from one to the other. That's basically all it is. So the two forms of Bernoulli that we'll use are for in a straight line, perpendicular to the flow lines. The first expressions in each of these are just written in differential terms. So it's rates of change of this. Basically they say that the rate of change of pressure, if you change the pressure in the system, you also have to either increase the velocity or increase the elevation to be able to compensate for it. And so sometimes we might want to use them in differential form. But by far the better use of these is in this format. Okay? So that's just a simpler way of getting to the end point. So this is an important expression for us to use, which will kind of explain exactly what it means as we go through this. Okay. So what did I want to? No, I guess it's in this, right? So let's move on a little bit. So it means that we don't have to worry about this page, because that's what it is. We don't have to worry about this page. We don't have to worry about this page so much. We don't have to worry about this page. But let's look at what this physically means in a physical sense. So this brings in the analog between the guy on the ski jump or the Mini Cooper on the ski jump, is that you can imagine if you are going down, oops. So you're going along a road in a car, and that's fine. You're happy going down the road. Gravity acting on you is acting at the same as you would be here. But what happens when you go up over a bump? You know that as you go over a bump, if you go over too fast, you get airborne, and so gravity is reduced, right? Because you're being thrown up in the air. And so the question is, how would you calculate, for instance, how the pressure changes as you move up in this fluid? In this fluid, since we know that it's just moving in a straight line, there's no rotation, we would expect that the pressure distribution here would be equal to what? Unit weight times the depth, as we used it. So in other words, in this expression here, the rate of change of pressure, we've used this expression before, dP dz is equal to minus times the unit weight, which just, if you integrate that, we end up with this expression. So if you're in this flowing fluid, so now it's not static anymore, if you go down through this, you'd expect that the fluid pressure within here would vary with the unit weight of water. So I'm not going to prove that, but this is what this little proof does here. And what you can do is we're switching across streamlines, and so what we can use is the magnitude of the radius of curvature to be able to show that. So what we're going to do is we're going to do a little example to be able to figure out exactly, I guess the question is, what is the change in fluid pressure as we go across here? Is it equal to P equals H times the unit weight? Oops, I'm not doing that very well. Or is it P equals H plus something times the unit weight, which would be linear? Or is it some other thing? We don't know. So let's use the expression that we have to be able to explore that. So this little piece of the notes here kind of explores that, but let's do it in a little more detail, because I think this is important. So this is to try and explain using the expression that we've just got. The expression we just had, well, we divided through by unit weights, but let's not do that here. So this is the expression that we just got. what we can do is we can write that expression on one streamline. So this is one streamline that goes here, and a parallel streamline is going through here. And our quest is, if you like, to figure out exactly how pressure changes as we go from one point to another. And our reason for doing that is if we know that the pressure here has to be atmospheric, if we know, so pressure 4 is atmospheric, if we know this, then hopefully we can figure out exactly what P3 is, pressure at this point. So what we can do is we can write Bernoulli's expression with this curvature in it for these 2 points. So we can write it at point 4, which is just this expression here. This is the expression we just derived. And so it would be the pressure at this point, which we actually know is atmospheric, but let's not worry about that yet. It would be the density of the fluid that's flowing. It would be the radius, average radius of curvature. So some average radius. So this radius would be from the center of curvature here to some middling point. And we can get this, the magnitude of this integral from this. In fact, actually what we'd like to do is this would be R4, and this would be R3, right? Just, these are all on a circular arc. So we can get this. We know the elevation of this. So our coordinate system is, let's take the center of our circle as z equals 0. Z is always positive upwards, but we said this direction of n that we're using is always pointing into the center of rotation. So we need to be aware of that this magnitude here is pointing towards the center of rotation. So we can write this expression at point 4. We can also write the expression at point 3. We know that each of these expressions are equal to a constant. Even though they're not on the same streamline, they're orthogonal to each other. They're equal to the same amount. And so what we can do is we can look at these 2 integrals here. So what do we know about this? Well, we know that if we subtract this integral over to the left-hand side, then we can write this as, this is the one on the left-hand side. All we've done is we've changed this value of dn to equal dz, right? Because this is dn, and the z direction is in the opposite direction, so that's the reason for this negative sign. We've done the same transformation here, and we just subtract one from each other. If we have 2 magnitudes where the limits, the bottom limit is the same, but the top limits are different, then that's just the integral between the gap, right? Nothing more than that. So this is kind of a standard result. And physically, all it means is if you're taking an integral of something, this is z. So if you have some function and you're evaluating it between z3 and z4, then the integral from z0 to this point here is just the area under this curve. So in other words, the integral, you know this, right? Integral z0 to z4 is just this ringed area. The integral z0 to z3 is this area. I know I can't do it much better, but you can probably do this better. This is the integral z0 to z3 dz, whatever that function is. And so subtracting them from each other physically is this area here. And that's all it is. So it's the integral evaluated between these limits. So it's good to get a physical feel for what this integral is. It's just, that's all it is. It's adding up the area underneath that distribution. I wish I had some better colors, but I hope you get the idea. So we can replace these 2 integrals with this one. And if we do that resubstitution, we end up with this expression here. What else can we do with this? Well, we said that this is on the upper surface. So if, in other words, remember it looked like this. This was point 4. This is point 3. Pressure at 4 we said was equal to atmospheric. So this is equal to 0. We don't know what this is. This is what we're interested in finding out. And so what we can do is we can rearrange it. We know that P4 is 0. We know that Z4 and Z3 are just different by this height. So this is H, what did I call it, 3, 4 here? Yeah, 3, 4. Right? It's just the separation between those places in the Z direction, in the vertical direction, which we have here, which we know if we know the geometry. And so we can resubstitute it in terms of this one parameter we want. And if we use that, then what we see is that we have the pressure at that point is equal to the unit weight of the fluid times the depth, which is normally the case if we just have a static fluid. Right? So this is 0.4, this is 0.3, and all this is saying that if this is pressure, then P is equal to gamma H. That's all, right? It's exactly the same as a static fluid, but there's this extra term that's added onto it. And so this extra term, we know what the radius of curvature is. The radius of curvature would be some number in here. So if we're interested in P3, we could choose a value of R. This is the center of rotation. This is the value of R. So if we know the value of R, if we know the value of velocity along the streamline squared, then we end up with some magnitude. So we need to know what this velocity is. But the bottom line is that this is going to be a term which is negative. And so it's going to be subtracted from this. And so this is always positive. V squared has to be positive, and radius is always positive. And so the integral of those between these 2 points also has to be positive. And so this is a negative amount. So we know that the value of the pressure distribution as we go on a curve that looks like this is going to be less than the case if it's a static fluid. Or if it's a moving fluid that's moving along with, if it's a static fluid. If the curvature is like this, right, it's different because now, oops, does delete get rid of that? No, it doesn't. I thought Control Z did, but apparently not. I guess I could do, no, I'm not going to worry about it. So I'm going to just draw it again. So if the curvature, if the velocity is like this, then the radius to the center of this is something like this. And so if it's going up on this kind of curve instead of on this kind of curve, then what we'd find out is that the magnitude of this term would be positive. And so in that particular case, didn't want to do that. Well, I guess that solved it. Full screen. And so if that were the case, then the magnitude of this term is positive. And so physically what that would look like would be this. So this would be for going into a hollow and coming back out. And so it kind of makes sense. What we haven't said is what the fluid pressure distribution would be if you are just going parallel to each other. We've kind of alluded to the fact that it might be equal to the static case, but we haven't really shown that. But what we have now is we have enough information to be able to show that because we know that this is a function of the radius of curvature. If the flow is horizontal and the streamlines are parallel to each other, then the radius of curvature of this is what? It's infinite, right? So when r goes to infinity, then this term is going to disappear because this term is vanishingly small. And if that's the case, then this term will not be there, and the pressure distribution will be just the linear pressure distribution that we have in a static fluid. The fluid is not static, it's flowing from your left to your right, but the pressure distribution will be that. And so that's why this expression is relatively it's not particularly straightforward actually, but it's an important expression for us to use. This is the expression that we've used, this is all we've used, and so make sure that you realize exactly what this means. The important things to realize, I think, are that the coordinate system that we use is always this, that there's a z direction which is always upwards. There's a radius, which is always to the streamline. Whoops. There's a velocity along that streamline, which is always v sub s. If you want to, you can call that v sub s. So there's the velocity along the streamline. It's not the velocity perpendicular to the streamline. So this is one streamline here. This is another streamline here. It can't be the velocity perpendicular to the streamline because there is no velocity perpendicular to the streamline, right? If you're going in a car at 5 miles an hour, the velocity of the car perpendicular to you is 0, right? If you're attached to the streamline. And so the flow direction is along the streamline only. There is no velocity in this direction. So this is the streamline velocity. This is the radius from the center of the rotation, if you like, the angle of rotation of this thing, which is this point here. R is always positive, and the direction is always perpendicular to this. So it's a little bit complicated, but if you remember those tenets, you basically, so Z is always vertical, N is always perpendicular to the streamline, it always points towards the radius, so maybe towards center, always. This is always positive, this is a streamline velocity, and this is the density of the fluid. And so given that, basically you can do is you can hop between streamlines to be able to figure out what the fluid pressure distribution is. And just to recap, if you look at pressure with depth from the surface, this is the pressure for R equals infinity, when the pressure distribution is equal to H unit weight, exactly the same as in a static fluid. This is the distribution if you're going into a hollow and coming out. And this is the distribution if you're going over a hump. And you can kind of rationalize those. So that's why we showed the mini and the ski jumper, because it's really analogous physics. You're going around a bend, you're being forced into that bend. You can imagine that if you're going off a ski jump, I never have, that your legs will compress because you're being forced on a particular arc. And that's exactly the same as this. You can imagine that if you're going into a hollow, which is this case here, your knees would compress, and basically the unit weight of your body, sorry, the weight of your body is increasing because G is increasing on you. That's basically what's going on, okay? So not a simple concept, but one that's kind of important to what we do. So you have that. So I'd encourage you to look at that at your leisure just to see that you understand it. Okay? Everyone okay? Questions? No. All right. So in all of these cases, what we're going to do is we can either write along a streamline, or we can write perpendicular to a streamline an expression. We know that it's constant, and so we can write the equation at 2 points. Those 2 points are either along a streamline, in this case, or they're going across streamlines in the case we need to deal with it. We talked about the conditions that are required for Bernoulli to be true. It has to be incompressible, which usually means it's a liquid, but it's also used for gases. We'll use it for gases as well. It has no viscosity. So inviscid means that viscosity is equal to 0. And so it depends on other conditions in the system, but it's easy for us to use it in liquids and assume that they are not very viscous. You wouldn't want to use it in lavas or magmas maybe, or in treacles and honey, but certainly in Newtonian fluids we can use it. And the other thing that was the requirement was its steady state. And so steady state means that if you look at any particular location at a snapshot in time, and you come back to that, take a snapshot 10 minutes later, the conditions at any one point haven't changed. Doesn't mean that the conditions everywhere are the same, but they don't change with time. So let's look at some applications for this, just for the linear, along a streamline Bernoulli equation. Because that's by far the most useful and most thoroughly used one that we'll deal with. Don't know what this is for. I guess I didn't want to do that. So the idea here is that if you put the physical meaning of this is that the sum of the pressure head, the velocity head, and the elevation head, as they're often referred to, are constant on any streamline. So if you look at a streamline going through a fluid, and this would be one streamline, do this, you can write the magnitude of that expression here, and they should both equal the same thing. That's all we're going to attempt to do with it. The physical meaning of this is that if you look at the velocity at this particular point, you can look at the behaviors, the pressure head, which would just be the height of water above this little piezometer tube, the elevation of it above some datum. So remember, in all of our stuff that we'll do, z is positive upwards. And you can choose any datum you want. You could choose this one. You could choose one up here and go down from it. It doesn't matter, but z is always positive upwards. If you take the magnitude of the elevation, and if you add that to the fluid pressure at this particular point, then you'd have two of these components, this one and this one defined. It doesn't necessarily mean that the velocity here is zero, but what you could do is you could test for that by actually staunching the flow. So this is how a Pitot tube works on an aircraft, which you better hope works if you want to get to your destination. And that is, it points in the direction of flight. And what it does is it takes the air that's traveling towards it, which of course is static, but the plane is traveling at an airspeed. So you could think of the plane as being static and the air coming past it. So think of a plane in an air tunnel where the plane's static and the air is coming past it is perhaps easier to think of. And so it kills the velocity at this particular point. And so what it does is it kills this velocity, and you'd expect the fluid pressure in this thing to rise as a function of it changing the magnitude of the velocity. And so this is one way that we could measure the absolute magnitude of this, which sometimes we'll call uppercase H, total head. So that's the expression we'll use. So this here comprises a magnitude of elevation head here, the magnitude of fluid pressure, which just is the depth below this, and if you kill the velocity from this velocity here to v equals 0 at this point, you get a rise in this thing because you're changing the distribution of behaviors, and the pressure at this point would no longer now be just the surface, it would be equal to this amount here, p over unit weight. So try and get a physical appreciation of exactly what's going on in this system. And that's really what we're attempting to use this for. Right? So, and we can always evaluate this. So typically we'll make this magnitude equal to some total head. And so our only interest is in being able to choose locations at different points, right in front of here, and also right up against this tube, and be able to rationalize exactly what the pressures are at those points. Okay? The point we've just kind of made in this is something which is apparent if you look at what's referred to as stagnation points. And stagnation points just mean that sometimes it's referred to as saltation velocity. So along this streamline, we have some velocity, and a long way away from this ball before it hits it, you'd think that the velocities maybe on all streamlines are probably about the same. But the one streamline that intersects this ball and then gets shot in two different directions, one that goes around here and one that slips around here, means that the velocity at this point as it hits this, it goes from some relatively big velocity, probably very similar to the velocity along here, to 0 because it's stopped by the ball. And so the stagnation point in this particular flow is exactly here, and it replicates the fact that the velocity goes from some magnitude to some other velocity, which in this case you'd expect to be 0 because it's basically a fire hose on a wall, and you know that the water isn't going through the wall. And so that's something that we can use. And so what that means is that the velocity of the fluid that's flowing into it all of a sudden becomes 0, and so the magnitude of this velocity head has to get transferred onto one of these other components. It can't get transferred on the elevation because it's equal to a big velocity here and a 0 velocity here. They're both at the same elevation, so this can't change. So this has to stay the same. So the only thing that can happen is that the fluid pressure goes up. And so in other words, you have a fire hose on a wall, the fire hose hits the wall, it's at the same elevation, elevation hasn't changed between just before it hits the wall and when it has hit the wall. And as a result, since the velocity goes from a big number to 0, it has to be shed onto one of the terms, and the only term it can possibly be shed onto is this one. And so you get pushed over by the fire hose because you have a pressure that was atmospheric when it's traveling at a very large velocity, to basically taking the v squared over 2g term, and all of the momentum of that jet is transferred into a pressure on your chest or on the wall or whatever it is. And so that's actually the mechanism, if you like. If we go back to where we were before, if you remember this, you'll remember our Jackass friend, right? I guess I might have to see if we can do this. So, try to refresh it, I guess so. Well, you know it. You've seen this before. Don't know why it doesn't want to work. Just thinking. Come on. So.
I'm Dave England, and this is the Fire Hose Rodeo.
Okay, that's our guy. So it's the fire hose rodeo. I think I can't draw on this, but this is a guy that's sitting on top of a hose, obviously, in which stuff is squirting out the bottom. And you could calculate, for instance, how much velocity you need out of this system to be able to keep him up. It's a relatively simple calculation. You now have the tools to be able to do that. And, oops, I won't play it. You can play it at your leisure. But if we look at this predefined component here, so let's do it. Let's calculate exactly how that might work, just for him. So where are we? Okay. So what are we going to do with this guy? Well, let's, instead of thinking of the hose coming this way, let's think it comes this way. And so there's some flow rate coming in here, which we'll call a velocity. And what we could do is we can basically evaluate the behavior by looking at, for instance, just this point here. And let's think of this point as equal to a free body diagram that does this. So this is Z1, this is Z2, this is point 2. I know you don't have Mr. Jackass to draw on, but this is points. We know that the elevation we want to have going upwards in the positive Z direction. And let's call this just height H. So let's just do a free body diagram. And so if we wanted to represent this guy, this is the column of water. Let's say the column of water has some cross-sectional area A, and it's of height H, and it would have a weight of water, and it would also have a weight of the Jackass sitting on it. And so what are each of these? The weight of water is area times height times unit weight of water. And what's the weight of Jackass? Well, let's use this simple expression that this is the unit weight of water times the volume of Jackass. Pretty much true, right? We float in water, we're almost neutrally buoyant, so our density, we're actually made almost all out of water in many respects, except for our bones, but we're essentially the density of water. And so that's just easy. And so this has to be resisted by a pressure, which is coming from the hose, by a force actually, which is equal to the pressure times the area on which it acts, and this is uppercase P, which is a force. And so we can write an expression that weight of water plus weight of Jackass equals P, which is unit weight of water times, times the height of the fluid column times the area of the fluid column plus the volume of the person is equal to the fluid pressure acting at the bottom multiplied through by the area. Okay? So what else could we do? We could divide both sides through by the area. And we could divide both sides through by unit weight. And if we do that, we end up with pressure divided by unit weight. It's the pressure, of course, at point number 1 is equal to the height times A over A plus the volume of the solid, of the person rather, divided by A. So this is just 1, obviously, right? Okay. So what we'd like to do is we'd like to be able to figure out exactly what the pressure is acting at this point. So what we can do is we could write Bernoulli at a couple of different locations. We could write it at point 1. So P over gamma 1 plus Z1 plus velocity at 1 squared over 2g is equal to some number we don't know. And we could also write it at the point where it impacts, P2 over unit weight plus, I guess I did this wrong, right? It doesn't matter. They're in the wrong place, right? Obviously. This is 1, which is the lower one, and the lower one is the upper one, but never mind. This is Z2 plus V2 squared over 2G is equal to the same constant. So these are equal to each other. So let's see what we know about these things. At P2, it's in atmosphere, so the pressure is equal to 0. The elevation is equal to h, and the velocity we don't know. At location 1, it's impacting this, it's turning all its velocity into pressure, basically. So what are the components here? At this point, we don't know the pressure. We know that the elevation Z1 is equal to 0. And we know that the velocity is all being killed because it's hitting the ground, and therefore this also is equal to 0. And so if we equate these things, we end up with P1 over gamma is equal to H plus V2 squared over 2G. This should equal this, and if we write them together, we end up with H, the height, V2 squared over 2G is equal to H plus the volume of Jackass. This is a volume divided by the area of the jet, which impinges. That's it. So what we've seen is that the height of this column doesn't matter. You could be 10 feet, 1 foot, it doesn't matter because it kind of cancels out on both sides. The weight of it gets bigger as you get higher, but also the force of the water hitting the ground gets higher because it's just falling under gravity after it's come out of the pipe. And so basically, this and this are thrown out, and we have V2 squared over 2G is equal to the volume of Jackass divided by the area of the jet. Right? And so you can put some numbers in for this. What's the volume of Jackass? How much does Jackass weigh? How much? A couple 100 pounds? 100 kilos, right? So the easiest way is this. So Jackass equals 100 kilos. 100 kilograms is 0.1 meters cubed if it's water, right? We're just using that. And so the volume of us, if we float in water, and if I weigh 100 kilos, I weigh 90 kilos. If I float in water, then my volume, equivalent volume of water would be just a little less than 1/10 of a cubic meter. And so this is about 10 to the minus 1. The area of the jet, well, I don't know what the area of the jet is, but if we just take it as a square, and this is about 4 inches, this is equal to 10 centimeters, which is equal to 0.1 meters. And if that's the case, then area is about equal to 10 to the minus 2. And so a quick number would be 10 to the minus 1 over 10 to the minus 2. The units are in meters cubed and meters squared, so the result is in meters. And this is also in meters. And so you could figure out exactly what the velocity of the jet you have to be able to keep you off the ground. Basically, that's it. Nothing more than that. And so this isn't completely esoteric. It does have some useful applications. It basically says that V2 squared is equal to 2g V volume times the jet area, and you can square root both sides to be able to figure out what the velocity is that you have to produce fluid at to be able to keep yourself off the ground, and you can do that calculation. It also says that if you, there's no influence on how high this jet is, so you can keep yourself equally easily 2 feet off the ground and basically 10 feet off the ground with the same velocity, which seems kind of interesting, but it's because the jet is free falling from the moment it comes out until it hits the ground. Gravity is acting on it to make it accelerate under gravity. And it says that if you double the mass of the person sitting on it, then you only have to increase the velocity by the square root of 2, which is 1.4. So if you double the weight of the person sitting on it, you increase the velocity only by a factor of 1.4 times rather than double. So it gives you some kind of impression of what the behaviors are. So that's a simple application of Bernoulli, and we'll leave it at that. Okay? Any questions? Great. Have a good and safe weekend.